students, let us continue with the asymptotic notations. In the previous video I explained about the theta notation. Now let us see the big O notation. So the big O notation is, let us take the two differentiable functions. The two differentiable functions are f of n and g of n, and say f of n grows with same rate and slower than, or not and, or slower than g of n. So this is the condition of big O. The function always grows with the same rate or slower than g of n, means it represents f of n is less than or equal to c into g of n. C less than or equal, equal means same rate, slower than, that's why it is less than or equal to symbol, and it has to follow the condition where n is greater than or equal to n naught, and c should always greater than 0 and n naught is greater than or equal to 1. These are the conditions. So n is greater than or equal to n naught, and c, the constant, should be always greater than 0, and n naught is at least 1. The starting input value you have to given as 1, at least 1. So that's why n naught is greater than or equal to 1. So this will be denoted as f of n is equal to big O g of n. Actually, logically, this statement is broken into two because it is less than or equal to is there. So that's why logically broken down into f of n theta of g of n, or f of n small o g of n. Why it is written like this? This statement is written, the big O can be represented like this. Theta of g of n means it always follows same rate. The growth rate is same here. And small o, the growth rate is always slower. The growth rate is always slower than, when you compare with two functions, the f of n growth rate is always slower than the g of n in the small o. This is a small o representation. And for theta, same rate. So this is splitted into two. This big O notation is splitted into two. This maybe it satisfies the theta or it satisfies the small o notation. Okay, let me take the graphical representation of this big O notation. So I said this is the input function. S is n indicates the size of the function, and this is the time it takes for the function to complete. So now I'm taking c g of n, and here this is a function f of n, and this is the n naught. So this is, you call it as, always the big O notation is slower than. So this is completely upper bound. The c g of n is always present in upper. It is present in f of an upper bound. Okay, so then you have to take, let's take c is 4 because this is the upper bound. So this completely is the upper bound. So let me write the asymptotic notations. G of n is an asymptotic upper bound. So this is asymptotic upper bound for f of n. So this is present asymptotic upper bound for f of n. Okay, so let me take the example, the same example. Let's take f of n is equal to 3n plus 2 and g of n is equal to n. Now what is the formula? F of n is equal to big O g of n. So if this formula satisfies the condition of f of n less than or equal to c g of n, where c greater than 0 and not greater than or equal to 1. So now substitute the values. 3n plus 2 less than or equal to, c is greater than 0 and it is present in upper bound. So I am taking C as 4. Assume C as 4. First I am writing C, G of n in this place of G of n, and 3n plus 2 less than or equal to 4n. Okay, assume C is equal to 4 because it is upper bounded. Now here 3n plus 2 is less than or equal to n, and n is greater than or equal to 2. So this is a condition for upper bounded, means big O notation. So the big O notation, here the n is greater than or equal to 2. Means the size of the function that she is greater than or equal to 2. Okay. So this is big O notation. So in the next video I will explain about the big omega notation. Thank you.